Hey, this is Horner, and we're going to look at 16.1. This is all about electric charge. And if you've ever seen the movie Jurassic Park, you've seen the little mosquito inside the amber. And they went into that amber and they tried to extract DNA, and you know kind of the rest of the story. The other cool thing about amber is if you rub that piece of amber on just any piece of fabric, it will attract little tiny objects, such as maybe bits of string or some hair. And so we say the amber is really just charged by doing that rubbing. So some of the electric charges really just go from the amber between the amber and the cloth. So there will be some positive charges that are sitting on one, and you'll have excess negative charge on the other. And I'll kind of show you how that works in a little bit. But our word electric actually does come from the Greek word for amber, which is electron. So that's a little bit of history just with electric charges. There are some important things that you'll see as we go through. They'll be in this kind of weird purple. It'll typically have a pretty bold font up top, and then it'll tell you a little bit about what it is on the bottom. So this is a pretty important fact. The net charge of a closed system never changes, so it will always stay the same. And in order to illustrate that, let's talk a little bit about electric charge. So whenever they do experiments with amber and other materials, when you charge things, you'll find out that those two things that you charge can either be attractive or they can be repulsive. So to explain a lot of the experiments that they've done, we've been able to conclude there are a couple different types of charge. There's either positive and negative. So Ben Franklin was one of the first people to do this. And when he charged things, he noticed that sometimes if he charged one little sphere that was hanging on a string one way and charged the other one the other way, so one is positive and the other one is negative, they would actually attract each other, so they would pull in towards each other. And then if he charged a couple of different things the same way, so he took two similar spheres, charged them the same way so they both had the same charge, he noticed that they did repel. The net charge on a system is basically just the algebraic sum. So we're looking at the positive and the negative signs, and we try to figure out what is that net charge of that system. So for example, if I had a positive 2 sphere and it was touching then a sphere with a negative 2 charge, then my net charge here would be 0. So it's basically just adding those together. And that's what we just did here explains the bottom. So things that are electrically neutral have equal amounts of both positive and negative charge, and therefore do have a net charge that is equal to 0. On the next slide, we're going to talk about the elementary charge. So the magnitude, remember there's two things to a vector. There's both magnitude and direction. So we're really just looking at the number here. The magnitude on a proton and an electron is the same. So we've always said that protons have a positive charge and electrons have a negative charge. And the value for that charge is extremely small. It's about 1.602 times 10 to the negative 19th. And so that is what we call the elementary charge. And you'll notice that there's not a positive or a negative in front of this. This is just the magnitude of the charge for a proton or for an electron. The net charge on any object is an integral multiple of the elementary charge. For example, if I have 2 protons, it would be 2 times the 1.602 times 10 to the negative 19th, and that would give you that 3.204 times 10 to the negative 19th coulombs. And that's how you go through and do more than just one elementary charge. This table goes through and does a pretty good job of showing you the difference between mass and electric charge. The electric charge on a neutron is 0, so it is neutral, hence the name neutron. The electron has a negative 1.602 times 10 to the negative 19th coulomb charge, and a proton is positive 1.602 times 10 to the negative 19th. So here's that elementary charge symbol again, but notice now we've put a direction on these, and we've said they're either positive or negative based on whether they're a proton or electron. Remember, a proton is more massive than an electron is. And you'll notice that the proton and the neutron are very similar in mass, just off by a little bit. But that electron is definitely less massive, but still holds itself in terms of charge. So these two charges here are essentially the same. That's a little bit more about mass and charge. So let's take just a good look at an example. This is example 16.1, and it says the magnitude of charge transferred. So you're walking across a carpet. So here you are, and you're walking across a carpet. It's a nice shag carpet. And when you do that, you actually pick up charges all over the outside of your body. Okay, we'll talk about what the charge on the inside of your body would be, but right now we have those charges on the outside of your body. You reach out to shake hands with somebody else, and when you do that, you discharge. So you send that charge towards them, and then that charge will then end up going down into the ground. So it says if the charge is transferred by electrons only, so that's a hint, how many electrons are transferred, and if your body has a net charge of -1 nanocoulombs, estimate the percentage excess of electrons. So here we know that the mass of electrons is only about 1/2000th of the nucleon. So most of the mass of the body is in nucleons. We can just assume that half of the nucleons are protons and the other half are neutrons. So when we do that, we'll be able to kind of use that statement. Here we go. Since we know the coulomb is the SI unit of charge, the N must be that prefix nano, and it does mean times 10 to the -9th. So it's very, 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 very small. We know the value of the elementary charge in coulombs, and it's 1.6 times 10 to the -19th. And notice that I've shortened it up a little bit. So 1.6, 1.602. Either way, I think you should be fine when you go through and do this. For part B, we have to make a first order, or just an order of magnitude, estimate of the number of electrons in the human body. So we'll do that when we get to part B. So that's our strategy. That's what we're going to try to use in order to solve the problem. So here's our solution. We know that that we have 1 times 10 to the -9th coulombs, and there's about 1.6 times 10 to the -19th coulombs per electron. So that gives us somewhere around 6 times 10 to the 9th electrons. If we want to know the number of nucleons in the body, we know the mass of the body is somewhere around 70 kilograms, and the mass per nucleon is somewhere around 1.7 times 10 to the -27th kilograms. So if you do that math, you end up with about 4 times 10 to the 28th nucleons. But remember, nucleons are both protons and they're also neutrons. And so we're going to do 1/2 of this number, and that gives us 2 times 10 to the 28th protons. So the percentage of excess electrons is then our 6 times 10 to the 9th, and that would be electrons, divided by 2 times 10 to the 28th protons times 100%, and we see that that excess is only about 3 times 10 to the -17th%. And that is the end of 16.1. So here's another really important fact, or a little important statement here. Attraction and repulsion. You know that like charges repel each other. So if I have 2 positive charges, they will push against each other, and they will want to move away from each other. If I have 2 negative charges, they will do the same thing. They will want to try to repel, get away from each other. But if I have a positive and a negative charge, they love to try to come in towards each other. So these two will try to move that way. So like we said, like charges repel, unlike charges do attract. Electric charge, we're going to talk a little bit about polarization. An electrically neutral object does have regions of positive and negative charge within it, and they're separated. Because they're separated, we say that this object is polarized. So a polarized object can experience an electric force even though its net charge is 0. For example, if I take, let's say that I've got me, there I am, I got a little bit of hair left, and I take a balloon and I rub that balloon in my hair, then what I'll do is I'll end up putting excess charge all over this balloon, and we might say that it's negative charge. If I get it up next to a wall and I put that balloon right up against the wall, those negative charges on the balloon will actually attract the positive charges in the wall, okay? And it'll leave the negative charges kind of on the other side. So we say here that the wall has been polarized. So it's got a region of both positive and negative. And that's really polarization in a nutshell. The net force on the paper, so what we're doing here is we're taking a rubber rod. we're probably rubbing it with some wool. So I'm going to take some wool, I'm going to rub it on the rubber rod. We're going to have electrons that we're going to move, or a negative charge will move to the rubber rod, and so the wool will have a little bit of positive charge left over. If I take that rubber rod and I get it close to some little tiny paper bits, it will then make the paper polar. So we'll have a positive charge on one side, and then we will have a negative charge on the other. When they're really close to each other, we call this polarization by induction. So we're really not touching anything here. The other thing we can do is we can take some silk and we can rub it against a glass rod, and what will happen is now we'll have electron movement or negative charge movement towards the silk. That'll put some excess negative charges on the silk. It'll leave the glass rod with a positive charge, and then if I get it near those paper bits again, we'll have a polarized piece of paper where we'll have negative charge on one side and positive charge on the other. So we're really just polarizing by a process called induction. Here in the magnifying glass, they're showing you that it's not just this side and this side. There's actually molecules on the inside that are lining up that way. And that is electric charge and looking at polarization by induction. The next slide shows you about water. Some molecules are intrinsically, so these just by their nature are polarized, and we know that water is one of those things, and water has a lot of different properties because of this polarization and because of what we call hydrogen bonding. So if you look at the actual charge on the molecule, the oxygen side would have a charge of about negative 0.7 E, and then each hydrogen atom would have a positive charge of about 0.35 E, and you'll see that on each side. So this thing tends to be more negative on this side and more positive on this side. Really, it's kind of the ends that are that way. So just a natural molecule that exhibits that polarization. Because hydrogen bonds are in water, this is what gives a little bit of surface tension. It gives us our fairly high boiling point, fairly low melting point, those type of things. Just kind of some different things that happen. So it's a liquid rather than a gas at room temperature. It's a large specific heat, has a very large heat of vaporization. It's less dense as a solid than as a liquid, so it floats. You freeze a lot of other liquids, you won't have that. They actually will sink. Has a very large surface tension, it exhibits strong adhesive forces with some surfaces, and it's also a pretty powerful solvent of molecules. So if you think about DNA and RNA and proteins, same type of thing happens. You've got those hydrogen bonds, so if we have adenine and thymine, when they are bonded together, we're using hydrogen bonds to do that. So we're looking a lot of life processes actually use this electric charge, and some different types of bondings that come from polarization or polar molecules. And that is the end of section 16.1. 16.2 we'll do next, and it's about electric conductors and insulators.